Hi and welcome to DCO. My name is David Copete. In today's video, I'll be sharing with you this exercise. We start by creating the base rectangle, then extrude it and create a hexagonal grid, which then we turn into a circular pattern with a curve attractor. So if you are new and have never used curve attractors, this is going to be a good one for you. But if you have any questions or get stuck anywhere, you can download this from my website. So thank you very much for being here. Let's get into it. All right, the first thing we're going to do here is bring in a rectangle. So we'll go here, bring in a rectangle. Then here with this rectangle, we can explode it. But let's give it a size. So let's go here to 20.5, or just 20 and 2 decimal points. This is going to be for a square. So there would be different steps that you would take for a rectangle, like making sure you know the difference between the X and Y size, because that's going to determine your subdivisions for the grid. So once we have this, we'll pick an item. So we'll go to list item and pick just one of those line segments. With these lines, with the line segment, now we can extrude this in the Z direction. So we'll go extrude unit Z, and then I'll change the height to be, let's say, 50.0. So now the aspect ratio, let's say if we said 50, this would be a 50 by 100, so 1 to 2. So what we can do now is divide or isotrim this surface into smaller subdivisions. So we'll use isotrim. We'll also use divide domain squared. And now we can plug in that surface both into the domain and into the surface, and then the segments into the domain. Now we can change the U and V count. Now here's the thing. The U and V count, for them to maintain the aspect ratio of a square diagonal grid, you actually have to account for the aspect ratio. Otherwise, it's going to be a elongated grid, and sometimes you don't want that. So what we need to do is do 50 divided by 10, or just division, and then we'll go 10.000. And then we'll be doing the same thing to the Z count. And here's the reason why, because now we have a smaller number of 10 and 5. And we know that that's the aspect ratio. So if we go here, 10 and then 5, now what we need to do is decrease this number and the aspect ratio will maintain, because we're using a factor based off of the size of the original surface. So with this, we're going to extract all of the points that are at the intersections and also the midpoints. So first, area component, which gives us the midpoint. And then if I were to explode this and extract all the points, what happens is if you bake this and you look at your objects, these are individual. So since there are 4 surfaces here, there will actually be 4 points that are overlapping right at that intersection. So we don't want that. What we need to do is join those. So brep join. And once you join it and you deconstruct it, then you'll have the true amount of points within that brep. So now it'll be 153. And I can route that through a empty point component, as well as this one through a point component. So we know those are the points that we're working with. That's not necessary, by the way. You could just use the points from here, use the points from there. And now we're going to merge or put together this set and this set. But notice that if I were to put the circle right at the edge, well, it will not be within the surface. So for now, let's disable the preview on all of this stuff. And let's focus on offsetting the outside face of this. So if we go to VREP edges, and we join the exterior curves, the reason why we join it is because when you get the BREP edges, you actually get them as individual edges. And now this is a closed BREP that we can offset. And now it's offsetting to the outside. So we'll make sure to offset to the inside by negative, and then we'll give it a number. We'll just say 1.5. Now this polyline can be turned into a surface. So using boundary surfaces, we can build that surface again. And then here we can do this. Double click on the output. And now we'll plug this one outside of the relay, because now we can take the original surface and override it with the offset one. But notice what happens is the aspect ratio gets flipped. So now what we need to do is switch between the U and the V. So those are the things to keep in mind. Is sometimes when you rebuild something like a surface, if you have the different aspect ratio, then you have to flip these, but it'll still work. Okay. Now, at this stage, we can bring in some planes or some reference planes, an X, Z plane, and place them at every single one of those points. So let's go to an X, Z plane, plug that into the input, and now we'll go to circles using a plane input. And then the radius is going to be whatever it is, 1.5. And you're going to now see why I had to do some of those things. Let's say you want it to be this, the circles to be this large. Well, we can change the aspect ratio here to be larger. Let's go to 20. And this will click as to why we're doing some of this stuff. Notice that we're still outside of that. So this is where we bring the offset and offset it to the inside a little bit more. And now let's say we can change the size of these circles. And what I find cool about this is this aspect ratio part, that we can change it, keep it square, and then change the size of the circles. And then if we are still too far out or too far in, then the offset takes care of that. Now here's the thing. If you do want it to cut out that, well, there are things that we can do, but they are very computationally intensive, which means that it won't be as responsive as you'd like it to be. So with this being said, let's go back to here to where they're within. Maybe the distance between this and this is the same as that. So just make sure that we get it offset correctly. And now what we're going to do is recreate this surface using boundary surfaces. So boundary surfaces, which creates a surface, we'll use the outline that we have into offset, and then using the circles as the input. Now here's what we have to do. We have to flatten the output to make sure that it works, and we also have to flatten this input so that we know that it creates it as 1. And notice here that if you do have your profiler, so if you have display profiler, you'll see that 96% of the time that it takes to computate this script is taken up by creating this design. Now what we need to do now is take this and do it to all of them or rotate it. So there are different ways we can do this. We can rotate relative to the midpoint. So where do we get the midpoint? Well, when we use this, we can use an area component. Rotate, it's going to be the centroid is going to go into the plane. This is going to go into the geometry, but we can only create one. If we wanted to create 4, this is what we do. Quotation mark, 360. So 360 degrees divided by how many does the rectangle have? 4. So we can consistently say set data item to 4. So 360 divided by 4 is 90. And now we're going to create a series of rotations using this step and creating 4 because that's a consistent number. So now we have 0, 90, 180, and 270, and those are the degrees that we want to rotate this by. So now the cool thing about this is we're only creating one surface and then rotating it around. So it's not so intensive on the computer to have to subtract all of those circles away from one surface. Now let's go back here and let's change this up. And let's change the offset. And they all happen at once here. So what we're going to do now is look at our pattern, and now we're going to be creating the attractor, right? This is just a regular pattern that we can change using this. And now we want it to be vary depending on where a line segment is. Now the cool thing here is that we already have this line segment and we already have the height here. Technically we can evaluate a point and move it up and down, or just take this and move this up and down using a z unit z, and then use a number. So we'll go 5.50, or change the limit, let's say to 100, since that's actually the height. And now we'll leave it here at the bottom. Okay. Once we have that line segment, well, we need something to react to it. So what we use to react to it is going to be our set of points here. So these points and this, now we'll use a component called curve closest point, where this curve, it evaluates where this curve is and how close it is to all of these points. Now you have to make sure that the input is flattened, which means that they come in as just one long list. So let's go here to point. And then flatten the output here. Okay, why? Because now we're going to have 77 different numbers, and they're all going to depend on how far this curve is to that whole set of grid. So that being said, now we're going to take these numbers and we can plug them into the distance. Let's see what happens. They're too big. So what we need to do is make sure that we set a range between, let's say, between 1.5, or let's say 0.5 and 3.3. So let's do that. We'll remap numbers, because if we look at these numbers here, they're 77, not, well, the first one is not 8, 19, 30, 41, so they're too large. So to remap them into smaller numbers, we do bring in 3 different components: bounds, construct domain, and so this is how we plug them in. Distance goes into the value, and then distance also goes into the numbers, into the bounds, giving you the minimum and maximum, because we need the 91 to be a smaller number and the smaller number to be a smaller number. So now that goes into source. And now we're going to target the minimum and maximum. So one trick that I like to use is whatever component number you were using before for the circle that was working, that would probably be your max. And then copy this and lower this to 0, or 0.5, so we don't go to exactly 0. And now you'll see this. Now there are still 77 numbers that we have, but they changed by very little. 0, 1, 1.3, 1.7, 2.0. Well, now those numbers, which are 77 of them, and we have 77 values here. So what we need to do is flatten the input here so we know that they all come in as one list, and plug this into it. Because now we've remapped them to get smaller depending on how close this curve gets to it. So you can do your gradient backwards, you can do it this way, and you can also flip your directions. So if you want it to be large to small, or small to large, these are the kind of things that you need to be aware of, just if you're using point attractors or curve attractors too. So let me organize this. Okay, let's see the points, disable preview. And if you see that there's still some space for them, well, you can do that. Obviously, there's a limit to these. Like if you go too large, right? Now let's decrease the size. And let's increase the aspect ratio, or create smaller subdivisions like this. We'll just say 5 here. Let's see if it lets us. And now we'll go back and decrease the max. And the minimum. Not to 0, we'll do 0.1. And then going back to our offset. So these are things that, need a little bit of work. So let's okay. All right, so that's looking good. I'm going to actually move the curve attractor to the middle. Now we can take, now that we've created this surface, well, when we rotate it around, since we did an override with this one, now when you rotate it, now you get that effect on all of them. Now we can lower this, like I said, to the bottom. Now you have a gradient like this. So let's actually decrease the subdivisions. All right, let's see here, 10. Now we're going to go to this number. An elevation view, sometimes it's easier to see things. And then the offset, broke it. Now let's increase the size of them. And the minimum size too. So what we can do now is, since we know we have this one rotated around, let's extrude this surface, which is our original one. We can extrude it in the negative y. So we'll go y, negative. We'll go, let's see, 1.5. And if we use that to rotate it all the way around, well, we know that it will turn all of them into a solid. Here's the catch. When you do that, you actually have these corners that extend to the outside. So let's see how we can fix that issue. All right, so the idea here is if we go extruded in the positive direction, we will have overlaps here. So this is where I would say when you have all of them rotated with a certain amount, let's say if this was 2, then the frame here we need to be at least 4, which is twice as much. So just keep in mind that if you're going to be creating a large gradient like this, in some instances they will overlap, but if you make sure that the tolerances are right here, then we can actually join those together using union. So solid union, flatten the input, and merge all coplanar faces, which will get rid of the crease here at the top as well. So with this, now we've created a box that is fully parametric. We can change the depth of it and use a curve attractor to change where the pattern is located and change the gradient. So this could function as a skin. It could function as a container box. There are many different applications that you can use for this. I just wanted to share with you guys. And also this was a specific question that I got asked on my website. So if you have specific questions that you need help with, this is the kind of stuff that I can create videos for and share with you guys the entire process. So lastly, what we'll do is we'll take this, the last B-rep. Here's the thing. This B-rep here with merge all coplanar faces, it's not that common, but it's a very useful one to get rid of the creases. Now with that one, we'll go to custom preview and then change the color using color swatch or color picker, which actually gives you sometimes a better result. Now notice that we can still change some of these parameters like the offset. Let's see what happens if we offset it to where it intersects it. And then let's lower this. So what I'll be doing now is cleaning this up so you guys can download it, and I'll also be turning this into a cluster so you can have just the inputs and outputs to use with. So if you found this useful, let me know in the comments below. If you got lost or if you have any other questions, let me know. I would love to answer this for you. And what I do is I provide YouTube tutorials and resources for you guys that are into parametric design. So thank you very much for being here, and I hope to see you on the next one.